When dealing with electrical feeders and taps, it's important to understand the limitations in the main feeder. There are several key factors to consider, including current rating, overcurrent protection, voltage drop, and impedance. Firstly, the feeder must be rated to carry the full load of all the taps plus any additional load that may be added in the future. This means carefully calculating the total amperage that the feeder will need to supply and selecting a conductor size that can handle that current safely. Secondly, the feeder must be protected by overcurrent devices, such as fuses or circuit breakers. These devices are sized to trip at the feeder's current rating, preventing overloads and short circuits that could damage equipment or cause a fire. The overcurrent protection ensures that the feeder is protected from excessive current draw, which could lead to overheating and potential hazards. Thirdly, voltage drop on the feeder must be within acceptable limits. This is especially important for long feeder runs, as voltage drop can become significant over distance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To mitigate voltage drop, you may need to increase the conductor size or use a different type of conductor with low resistance. Fourthly, the impedance of the feeder must be low enough to prevent excessive voltage drop and power loss. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. High impedance can lead to voltage drop and power loss, which can affect the performance of connected equipment. To minimize impedance, use conductors with low resistance and keep the feeder runs as short as possible. Now, let's consider a scenario where a feeder is fed from 480 volt 600 amp fuses and enters a raceway above a piece of equipment. A tap is made, and the tap conductors drop into an enclosure with a breaker to protect the tap conductors and the equipment fed. The feeder then continues in the raceway to another piece of equipment, where a second tap is made. Both taps meet the 10-foot tap rule specified in the National Electrical Code, NEC Section 240.21. Assuming that the feeder is sized appropriately, the 600 amp fuses at the entrance of the feeder provide adequate overcurrent protection. However, the voltage drop on the feeder must be calculated to ensure it is within acceptable limits. The impedance of the feeder is assumed to be low enough for the intended application. To perform a voltage drop calculation, you will need to know the length of the feeder, the current it carries, the conductor size and type, and the power factor of the load. There are several online calculators and software tools available that can help you with this calculation. The NEC provides guidance on acceptable voltage drop limits. For example, NEC Section 210.19. 8.1. Informational Note Number 4 recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. These are recommendations, not mandatory requirements, but they are good guidelines to follow. If the voltage drop calculation reveals that the voltage drop is too high, you'll need to take steps to reduce it. This may involve increasing the conductor size, using a conductor with lower resistance, or shortening the feeder run. In addition to voltage drop, it's also important to consider the ampacity of the tap conductors. The tap conductors must have an ampacity that is at least 1/3 of the ampacity of the feeder conductors, according to NEC Section 240.21. D1. This ensures that the tap conductors are adequately sized to carry the load they supply. Furthermore, the tap conductors must be protected from overcurrent at the point where they connect to the feeder. This is typically done with a circuit breaker or fuses in an enclosure located near the tap point. The overcurrent protection device must be sized to protect the tap conductors and the equipment they supply. In summary, when working with electrical feeders and taps, it's crucial to consider the limitations on the main feeder. These limitations include current rating, overcurrent protection, voltage drop, and impedance. By carefully calculating these factors and following the requirements of the NEC, you can ensure that the feeder is safe, reliable, and efficient. Remember to always consult with a qualified electrician or electrical engineer if you have any questions or concerns about electrical installations. They can provide expert guidance and ensure that your electrical system meets all applicable codes and standards. Now let's delve a bit deeper into each of these aspects. Firstly, current rating. The current rating of a feeder is the maximum amount of current that it can safely carry continuously. This rating is determined by the size and type of conductor used for the feeder. The NEC provides tables that list the ampacity of various conductors based on their size, insulation type, and installation method. For example, NEC Table 310.16 lists the allowable ampacities of insulated conductors rated up to 600 volts, based on an ambient temperature of 30 degrees Celsius. When selecting a conductor for a feeder, it's important to choose one that has an ampacity that is at least equal to the calculated load current. The calculated load current includes the current draw of all the equipment connected to the feeder, plus any allowances for future expansion. Secondly, overcurrent protection. Overcurrent protection is the use of devices, such as fuses or circuit breakers, to protect electrical circuits from excessive current. These devices are designed to trip or open the circuit when the current exceeds a predetermined level. Overcurrent protection is essential for preventing damage to equipment and reducing the risk of electrical fires. The NEC requires that all electrical circuits be protected by overcurrent devices. The size of the overcurrent device must be matched to the ampacity of the conductor it protects. For example, if a conductor has an ampacity of 20 amps, it should be protected by a 20 amp circuit breaker or fuse. Thirdly, voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Voltage drop is more pronounced in long conductor runs and when the conductor is carrying a large amount of current. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for acceptable voltage drop limits. As mentioned earlier, NEC Section 210.19 A1. Informational Note Number 4 recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals current times resistance. The resistance of the conductor depends on its length, size, and material. You can find the resistance of various conductors in NEC Chapter 9, Table 8. Fourthly, impedance. Impedance is the total opposition to current flow in an alternating current circuit. It includes both resistance and reactance. Reactance is the opposition to current flow caused by inductance or capacitance in the circuit. High impedance can lead to voltage drop and power loss. To minimize impedance, use conductors with low resistance and keep the feeder runs as short as possible. Also, avoid creating unnecessary loops in the wiring, as this can increase inductance. In addition to these four key factors, there are other considerations to keep in mind when designing and installing electrical feeders. These include grounding, bonding, and surge protection. Grounding is the connection of electrical equipment to the earth. Grounding provides a path for fault current to flow back to the source, which helps to trip the overcurrent protection device and prevent electrical shock. Bonding is the connection of metallic parts of an electrical system to create a continuous electrical path. Bonding helps to reduce the risk of electrical shock by ensuring that all metallic parts are at the same potential. Surge protection is the use of devices to protect electrical equipment from voltage surges caused by lightning or other events. Surge protection devices divert the surge current to ground, preventing it from damaging the equipment. By considering all of these factors, you can design and install electrical feeders that are safe, reliable, and efficient. Remember to always consult with a qualified electrician or electrical engineer if you have any questions or concerns. Furthermore, understanding the NEC sections related to feeders and taps is crucial. Section 215.2 addresses the minimum size and rating of feeder conductors. It mandates that feeder conductors have an ampacity not less than required to supply the load calculated according to Part 3 of Article 220. This includes provisions for continuous loads, which are loads where the maximum current is expected to continue for 3 IOs or more. In such cases, the overcurrent protection device and the feeder conductors must be rated at 125% of the continuous load. Article 220 provides the requirements for calculating branch circuit, feeder, and service loads. It gives detailed instructions on how to determine the demand factors and load factors for various types of occupancies and equipment. Understanding how to apply these load calculation methods is essential for properly sizing feeders and ensuring that they can handle the expected load. Additionally, Section 215.3 covers the requirements for feeder overcurrent protection. Feeders must be protected against overcurrent in accordance with their ampacities, as specified in Section 240.4. This section provides detailed rules for selecting the appropriate overcurrent protection device based on the conductor size and type. It also addresses situations where the conductor ampacity does not correspond to a standard overcurrent device size, allowing for the use of the next higher standard overcurrent device rating under certain conditions. The tap rules outlined in Section 240.21 allow for the use of smaller conductors to tap off of a larger feeder, provided that certain conditions are met. These conditions include limitations on the length of the tap conductors, the ampacity of the tap conductors relative to the feeder conductors, and the overcurrent protection requirements for the tap conductors. The tap rules are designed to provide flexibility in electrical installations while ensuring that the tap conductors are adequately protected from overcurrent. When applying the tap rules, it's important to carefully consider the specific requirements for each type of tap. There are different rules for different tap lengths and applications. For example, the 10-foot tap rule allows for tap conductors up to 10 feet long without overcurrent protection at the tap point, provided that the tap conductors have an ampacity of at least 1/3 of the feeder conductors and terminate in a single overcurrent device rated no more than the ampacity of the tap conductors. The 25-foot tap rule allows for tap conductors up to 25 feet long under certain conditions, including increased ampacity requirements for the tap conductors and specific overcurrent protection requirements. It is important to note that these tap rules are not a substitute for proper feeder design and load calculations. Even when the tap rules are met, the overall feeder must still be sized to carry a total load of all the taps and any additional loads that may be connected to it. Moreover, the voltage drop on the feeder must be within acceptable limits, regardless of whether tap rules are being applied. The NEC also addresses the use of flexible cords and cables for connecting equipment to feeders. Section 400.5 specifies the allowable ampacities for flexible cords and cables based on their size and type. It is important to ensure that any flexible cords or cables used in a feeder system are properly rated for the intended application and are protected from physical damage. The NEC also contains requirements for the installation and support of feeder conductors. Section 300.11 requires that raceways, cable assemblies, and cable trays be securely fastened in place. This helps to prevent damage to the conductors and ensures that they are properly supported. Section 310.15 provides requirements for derriting conductors when they are installed in close proximity to each other or in high-temperature environments. When conductors are installed in these conditions, their ampacity must be reduced to account for the increased heat. Understanding these NEC requirements is essential for designing and installing safe and compliant electrical feeder systems. It is important to consult the latest edition of the NEC and to seek guidance from a qualified electrician or electrical engineer if you have any questions or concerns. In addition to the NEC, there may be other applicable codes and standards that apply to electrical feeder systems. These may include local building codes, fire codes, and industry standards. It is important to be aware of these codes and standards and to ensure that your electrical installations comply with them. Furthermore, proper documentation is essential for electrical feeder systems. This includes maintaining accurate records of the feeder size, conductor type, overcurrent protection devices, and load calculations. This documentation can be helpful for troubleshooting problems and for future modifications to the system. Regularly inspecting and maintaining electrical feeder systems is also important. This includes checking for loose connections, damaged conductors, and signs of overheating. Any problems that are identified should be addressed promptly to prevent more serious issues from developing. Remember that electrical work can be dangerous, and it is important to take precautions to protect yourself from electrical shock and other hazards. Always to energize circuits before working on them, and use appropriate personal protective equipment, such as gloves and safety glasses. Finally, consider future needs when designing an electrical feeder system. Allow for future expansion by sizing the feeder to handle anticipated load growth. This can save time and money in the long run by avoiding the need to replace the feeder later. Remember to always consult with a qualified electrician or electrical engineer for any electrical work. They have the knowledge and experience to ensure that your electrical system is safe, reliable, and compliant with all applicable codes and standards. Let's illustrate with an example. Consider 480-volt, three-phase feeder supplying power to a manufacturing facility. The feeder is 200 feet long and consists of three 500 kc mil copper conductors in a steel conduit. The feeder supplies power to several pieces of equipment, including motors, lighting, and HVAC systems. The total calculated load on the feeder is 300 amps. To ensure that the feeder is properly sized, we need to consider the current rating, overcurrent protection, voltage drop, and impedance. Firstly, the current rating of the 500 kc mil copper conductors is 380 amps, according to NEC Table 310.16. This is greater than the calculated load of 300 amps, so the conductors are adequately sized. Secondly, the feeder must be protected by an overcurrent device. According to NEC Section 240.4, the overcurrent device must be sized to protect the conductors. In this case, a 300 amp circuit breaker would be appropriate. Thirdly, we need to calculate the voltage drop on the feeder. Using a voltage drop calculator, we can determine that the voltage drop on the 200-foot feeder is approximately 2.5%. This is within the acceptable limit of 5%, so the voltage drop is not a concern. Fourthly, we need to consider the impedance of the feeder. The impedance of the feeder depends on the length, size, and material of the conductors. In this case, the impedance is assumed to be low enough for the intended application. In addition to these considerations, we also need to ensure that the feeder is properly grounded and bonded. The grounding and bonding requirements are specified in NEC Article 250. By considering all of these factors, we can ensure that the 480-volt feeder is safe, reliable, and efficient. And now let's talk about demand factors. Demand factors are multipliers used in electrical load calculations to account for the fact that not all electrical loads operate at their maximum ratings simultaneously. The NEC allows the use of demand factors in certain situations to reduce the calculated load on a feeder or service, which can result in smaller conductor sizes and overcurrent protection devices. Demand factors are based on statistical data and engineering judgment and vary depending on the type of occupancy and the types of loads being served. For example, a dwelling unit typically has a lower demand factor than a commercial building, because residential loads tend to be more diverse and less likely to operate at their maximum ratings simultaneously. The NEC provides demand factors for various types of occupancies and loads in Article 220. For example, Table 220.42 provides demand factors for general lighting loads and various types of occupancies. Table 220.53 provides demand factors for household electric ranges and cooking appliances. When applying demand factors, it is important to carefully consider the specific requirements for each type of load and to ensure that the demand factors are appropriate for the application. It is also important to document the demand factors used in the load calculations. Using demand factors can result in significant cost savings by allowing for smaller conductor sizes and overcurrent protection devices. However, it is important to use demand factors judiciously and to ensure that the feeder or service is still adequately sized to handle the expected load. In some cases, it may be more appropriate to use a load factor instead of a demand factor. Load factors are the ratio of the average load over a period of time to the peak load during that same period. Load factors are typically used for large commercial or industrial facilities where the load profile is well known. In these cases, the load factor can be used to determine the average load on the feeder or service, which can then be used to size the conductors and overcurrent protection devices.